So the other concept that we kind of ran out of time explaining at the end was the graphical relationship between displacement, velocity, and acceleration, right? So the first idea is just velocity is displacement over time, and then acceleration is changing velocity over time. So not quite velocity, but basically the same idea. It's how does the previous thing change over time. So given this concept or given this relationship, what we should be looking at is if you have a velocity graph in time. So let's make up a random curve. What essentially you want to find is you want to find the rate of change or the instantaneous rate of change at a certain point, which means the tangent line at that point. So for example, here we have a line that just kind of barely touches the curve, the velocity curve at a point. So that is considered a tangent line. So if we were able to find the slope of the tangent line, it would give us the instantaneous rate of change of that function at that point. So in this case, if you think about it, the vertical height of this tangent line we're drawing is really a changing velocity, right? Because if you think about it, it's the changing y value from here to here. So that's a change in velocity. And then the run of this graph, which is in difference in x value, is just a changing time, right? So therefore, if we find the slope of this tangent line, we would be finding the changing velocity over time, which gives us acceleration. So from the velocity curve, if we were to find its slope of tangent line, it would give us the slope of tangent line, sorry, it would give us the acceleration, right? So that basically gives us the rate of change of velocity, which is acceleration. And so by the exact same relationship, if we want to go from displacement to velocity, we would also look at slope of the tangent line. So you'd be looking at the slope of the tangent line on the displacement graph. Right, so let me draw that real quick. If we had a displacement graph, if we were moving like this, if we were to find the slope here, right, that's the rate of your displacement changing over time. That would give us the velocity, right, which is slope of that line. So that's the first relationship. Now, if we were to go backwards on this relationship, so let's cut it in half real quick. So if we have the same three variables, displacement, velocity, and acceleration, if we were to go backwards, what you should recognize is, well, that means a times time gives us the changing velocity, and then velocity times times gives us the displacement, right? So what that means is if we had a velocity curve and that was at a constant value, so let's say it's at 5, and we do it over a time of 4 seconds, what that means is if we find this area here, right, that's underneath this curve, let's do this in blue, if we do 4 times 5, that area essentially represents the velocity times the time, which gives us a value here of 20. And so therefore that's your displacement, right? So the area underneath the velocity curve, if it's a constant curve, obviously is the displacement. Now the concept remains constant even if the graph was not a flat horizontal line, right? Even if you have this curvy looking shape, if we find the area underneath, so we have to be able to imagine here is imagine a bunch of smaller rectangles that are dividing up the area into smaller pieces. But for each of the pieces, you still do the height of the function times the time, right? So base times height to get each of the area of these rectangles. And it would still be velocity times time, which ultimately gives us the displacement. So the main concept is it makes sense when it's a constant function, and you kind of have to take my word a little bit for it, but it should make some intuitive sense that if you find the area under a non-constant velocity curve, it would still be the displacement because it is still the velocity times time, just kind of broken up into smaller chunks, if you will. Right. So given this relationship, and it's the same relationship from from acceleration to velocity, if you want to go back up a level, essentially, you would look at the area under the curve. And be careful here, because it's area under the curve, specifically, it's actually possible to have negative areas. And I'll show you that a little bit more in the example, but let me just draw one real quick so you can kind of see it here in the instruction video. If we had a velocity curve and it actually went something like this, right? What you would have is you'd have two area regions. You have this blue area region, which is the positive area because the velocity curve is currently above the x-axis. But once the velocity curve goes below the x-axis, you can still find the area here between the curve and the x-axis. But because now the velocity is negative, we're doing vectors, we're doing with directions, it is actually possible to have a negative value here that will cancel in part with the positive value or the positive area beforehand. So if these two triangles were actually the same area, you could say, for example, that after this period of time from A to B, the displacement, the total displacement would actually add up back to 0. Effectively, what this object is describing what this graph is describing is an object that's moving to the right for a certain amount of time, and then it kind of moves backwards with the symmetrical amount of velocity ending back up at the initial position. So you have a displacement of 0. Okay, so like I said, I'll give you some more examples in the actual instruction or example video.